everyone, this is Handlebar Fox. Today we're going to be using Python to illustrate basic formulas for mapping a square onto your screen. Formulas which will also let you stretch or move it to any position and rectangular shape you desire. First, let's start with the exact concept. Here's the situation. You have a theoretical object, a grid, and we're going to display it on another grid, to be exact, the user's screen. This is a mapping problem. In other words, for every point in the grid, I need to determine the corresponding point on the screen. Since we're talking two-dimensional objects, we have two sets of XY coordinates. So given an XY coordinate of the theoretical object I'm working with, how do I transform that to the proper XY coordinate for my screen? In this video, we'll cover the most basic formulas which let you specify the starting and ending X and Y coordinates on the screen that define your grid, and then draw that grid using an XY of 0, 0 to whatever number we select in the grid itself. More on that in a second. First, let's follow one of the basic principles of mathematics and reduce our problem to its simplest version. We'll consider a one-dimensional case. Imagine our one-dimensional screen defined as a number line. This one is going from -10 to 10. Now, our object has its own internal coordinates going from 0 to 5. Let's say that I want to put the 0 point on -2 on the screen and the 5 point on 8 on the screen line. I need a function that will accept 0 and return -2. It accepts 5 and returns 8. But it also takes any value between 0 and 5 and returns the corresponding point in between. Here's the mapping for the whole numbers in this example. Our scale is 1 unit in our object equaling 2 units on our screen line, and it starts at -2. Given that, all we need to do for our formula is to say -2 plus x times scale, which in this case results in -2 plus x times 2. How do we determine our scale? Divide the difference between our screen points, 10, by the difference in our internal object's points, 5. So the general formula would be starting point plus x times screen ending point minus screen starting point divided by internal object ending point minus internal object starting point. Substituting our values back in gets us to our original formula. But enough theory. Time to write a simple Python program that illustrates all this. The actual source code is in the description, but I'll go through it briefly here. First section. Import turtle is the command to load our drawing library. Next, we set up the min and max X and Y coordinates on our screen to map our grid onto. Resolution tells us the size of our object. So for this example, we're following the simplified form of our object starting at 0 and going up to, in this case, 4. It's important to note that these numbers are the ones we get to change when we run our demonstration here in just a minute. Next section, this is, well, the exact details of what's going on here aren't really relevant to our discussion. The comment pretty much says it all. We're setting the screen up for the pen and we're defining a few essential characteristics. One thing that is relevant is that the screen is 600 pixels wide and 600 pixels high. This function is the Python commands to go to XY on the screen and draw a dot of the specified RGB color. Note that these X and Y numbers are mapped to our screen, which again is 600 pixels wide and high. It has 0, 0 in the middle, so the numbers go roughly from -300 to 300 in both directions. This function is a little extra fun I had with the program. In theory, a simple black dot would illustrate much of what we need when we map our grid onto the screen. But this decides on a color for each different dot that is drawn. It uses 3 different gradients, one each for red, green, and blue. It looks pretty and also helps illustrate a few more things that you'll see in a minute. This is the key to our whole discussion. Translating our one-dimensional formula from earlier into 2 dimensions just means doing the same formula for both x and y separately. Note that the scale calculations just divide by resolution instead of the more general formula of calculating the difference between the begin and end values of the internal object. We can do that because we're arbitrarily defining it as starting at 0, as in our example earlier, so resolution minus 0 is just resolution. This is the set of loops that actually draws our grid, one loop inside the other. It will go from min to maxX, and inside that loop it goes from min to maxY. The resolution plus 1 in the range command is necessary because the range command is actually being used for the actual number of dots drawn. We're drawing both ends of our objects, so the number of actual drawing steps we take is one more than the size. In this case, an object of size 4 goes from 0 to 4, which is a total of 5 dots. And the last statement holds our completed drawing on screen until we click on it. Now, let's see it in action. Alright, let's run our program now and see what we get. We start at minX, minY. We go from minX to maxX, and inside it we went from minY to maxY. We start with a blue dot and we end with a yellow dot. That's simply how the coloring scheme I created works. One thing to note shows up down here. Let's get rid of this by clicking on it. Last line in the program. And let's look down here. We have numbers. Where do these numbers come from? They come from the line in the program I did not mention during our walkthrough. It's this one right here in the transform XY function, which takes the XY from the inside of the grid and translates that to the screen coordinates. It prints both of those down here. So 4, 0 in the grid coordinates equals 250, negative 250 in screen coordinates. This is a great way to see exactly how things translate number-wise. It's also a great way to help debug things if your formulas aren't working, and to be blunt, that's why it's there in the first place. Okay, now that we've got that out of the way, let's try playing with our parameters and see what we can do. The first thing I'm going to try is shrinking our grid. So we're going to change all these 250s down to just 50. This makes the grid much smaller, but since we adjusted everything equally, it's still centered in the middle of the screen. There we go. Started at blue, went to yellow. Looks exactly the same before, drawn the same way as before, just on a smaller scale, because I defined it to be smaller here with the minX and the minY. It was still centered simply because I chose to adjust them all evenly. Let's choose to adjust unevenly. We're going to take the minX and minY and we're going to go back down to negative 150. We'll leave the maxX and maxY at 50. This moved the blue from up around here to down here, but left the yellow where it was. We're still a square because they are equal, defined that way, but the center of it has been moved off of the origin point. Now, there's nothing that says, truthfully, that the minX and minY have to be numerically less than the maxX, maxY. That's a useful way of thinking about it, but the way these formulas are drawn, they can handle it being the other way. And to illustrate this, I'm going to take this blue dot here, which is at negative 150, negative 150, and I'll move it up here. To do so, I have to go up in the y direction, so I'm going to change the negative 150 to a positive 150, which I will note is actually greater than the so-called maxY of 50. And there we go. It's drawing a rectangle, but instead of starting down here, it starts up here. Our minX maxX is still working the same. The minY plus the maxY is really, it's reversed in terms of naming conventions. At this point, what you should probably realize is that minX minY defines where we start, blue dot. maxX maxY defines where we end, yellow dot. Okay, let's try one more thing. There's a number we haven't touched The minX, minYs, we've adjusted them all over the place. We've left this resolution unchecked, or I should say unchanged. So I'm going to change that 4 to a 9. This will draw our grid in greater detail. As you can see, there's many more dots. Instead of being 5 by 5, essentially it's 10 by 10 for the number of dots drawn. It looks very pretty, but it did take significantly longer to draw. This brings up an important side point. The turtle library that comes with the Python language is great for simple drawings. It's great for simple concepts. If you're ever serious about doing graphics with a Python program, you're going to have to find a graphics library that is better performing, shall we phrase it that way, than the turtle library, because it takes forever to draw anything that is complicated. And with that, I believe we can end this part of the video. But wait, there's more! Next time. Stay tuned for the next video where we see the basic techniques for rotating a square grid. So, till next time, see ya!